Welcome to Lab 4. Let's get started. In this lab, we're going to predict the behavior of various circuits with resistors and capacitors, and we're going to simulate these circuits using virtual labs and measure conventional current and potential difference. The key principles that we're using are Kirchhoff's junction rule, which states that the sum of the current going in is the same as the sum of the current going out for a particular node in a circuit. The next one is Kirchhoff's loop rule, which states that the sum of the potential difference for a closed circuit path or loop is 0. And we have Ohm's law, which is the potential difference is the same as the product of the current time. So in order to save time, we'll run through this one pretty quickly. This is our first circuit. It's got two batteries, two resistors. We're measuring the current at two different locations through ammeters. And by using Kirchhoff's loop rule, we know that the sum of the potential differences through this entire loop is 0. And we know that the current going in at a particular node is the same as the current going out. So doing a little bit of math, we can determine that the current going through the ammeters 1 and 2 is the same, and that value is 0.02 amps. So here are some variations of this simple circuit setup. On the far left, we see our initial setup. In the middle, we see switching the leads for the ammeter, and we don't notice a change in value, which is surprising. I would have expected it to go negative, but I digress. And then on the far right, we see a voltmeter hooked up. Now, a voltmeter has a very high internal resistance, hence why the ammeter is reading 0 amps, and it's reading the potential difference that is the same as the two batteries. Next, using the same setup, we're going to take a look at the potential difference across a number of different points. So on the left is our setup of where we are taking these measurements from. The middle shows the graph of the potential difference, and the right shows a table with our measured values. So there's a couple key things that we need to take a look at. First of all, you'll notice that there's quite a few locations where the potential difference is 0. This is because our wires and ammeters are simulated to be ideal, so they have no internal resistance. From A to B, we see a jump of 3 volts, which is expected. It's applied by two batteries with 1.5 volts each. And from C to D and E to F, we see a negative change in potential difference, which makes sense. It is caused by the resistors. And another key thing to take a look at is the sum of all of our potential differences is 0, which adheres to Kirchhoff's loop rule. In addition, we measured the resistance values for the first and second resistors, and we found that they were actually slightly different. Instead of 4. The next thing we're going to test is the difference between ammeters and voltmeters. So when putting a voltmeter in parallel, we basically notice no changes in our ammeters. But when we put an ammeter in parallel, we notice that our current values change from 0.02 amps to 0.06 amps. So why do these values change? Well, a voltmeter has a very high internal resistance, so it doesn't alter the current readings. But an ammeter has a very low internal resistance, and in our case, it has an internal resistance of 0. So as a result, in this circuit, instead of going through the second resistor, which is 100 ohms, the current just flows directly through this 0 resistance ammeter, and as a result, the 100 ohm resistor is basically bypassed or completely ignored in the circuit, resulting in the higher current flow. Next, we're going to dive into some RC circuits. RC circuits are just circuits that have a resistor and a capacitor. With this setup, we notice that when the battery is connected, the capacitor charges and the bulb illuminates and gradually fades over time. And when the battery is disconnected, the capacitor discharges and the bulb illuminates and light fades again with time. So from this, we can determine that light behavior corresponds with current. Another thing we can notice is the relationship between resistance and time it takes to charge and discharge a capacitor. So with a 10 ohm bulb, it takes approximately 10.3 seconds to discharge or charge. By doubling the resistance, we double the time. So this shows that resistance is directly proportional to the charge and discharge time of the capacitor. Here's where we do some cool math. So time constant of a circuit. The time constant is the same as resistance times capacitance of an RC circuit, and is the time at which the potential difference has dropped to 1 over E of its original value. So on the right, you can see a table that shows us measuring for 20 seconds the potential difference of the circuit as it's discharging. What we did is we plotted the natural log of the potential difference over the initial potential difference and plotted that with time. With that, we get a linear relationship. We can take the slope and find the reciprocal of it to calculate our experimental value for RC. We determined this value to be 5.9988 seconds, which when calculated is supposed to be 6 seconds, so that shows that we're pretty darn close. So now for the ending questions. If we'd use an actual ammeter in this lab, there is some internal resistance in a real ammeter, so it would cause a drop in potential difference across the ammeter and reduced current. And this is different than our simulation because our simulation has an ideal ammeter, so there's no resistance. And if we used a real battery to charge a real capacitor, the simulation would show the capacitor being instantly charged since there's no resistance in the circuit. In reality, real batteries and capacitors have small sources of internal resistance, so this would not happen. Thank you for watching.